Greetings and welcome to the lesson CTM students for 12.8. It can be found on these pages here in your book. Here's our new vocabulary for this one here. So we're going to actually, a review term right here, the counting principle, will get used again in this lesson. Permutations and the permutation formula and permutation formula for duplicate objects. We're going to learn about all those things within the context of this lesson. Make sure you use those extra examples in your book. For additional help, read those, actually look through those if you need some extra help. There's 7 more examples. We're going to do, I believe it is 4 together here. So the counting principle to start here. I'm not going to have you write it down again. It's already in your notes, or should be in your notes from lesson 12.5. So I just want to make a reference to that lesson to start. So counting principle, let's just write C, lesson 12.5 notes. And to remind you verbally of what that was, it was if something could happen in m ways and then another thing could happen in n ways, you can multiply those two things together. M times n is the total number of ways that thing can happen. We are going to use that in our first example here. And so this first example will deal with what you see over here. This is an old school California license plate, 1986. Wow, that is way back there. But typical California license plates are determined. You like that? My half singing, half reading right there. Yes, it's beautiful, I know. Are determined using 1 digit. 0 through 9 are the digits, so 10 digits to choose from, followed by 3 letters. So they did the same thing even back in the day, back in 1986. Digit, 3 letters, and then 3 more digits. So followed by 3 more digits. Here's the question: how many distinct license plates can be made if, and we're going to break this one down into some different parts and see some different variations on the problem. So part A, repetition. If repetition is allowed. If it's okay to repeat digits, if it's okay to repeat letters. So repetition is allowed. And it looks like this license plate, it was allowed. We have 2 C's here and here. We're going to assume for part A that it is allowed. Let's underline is and assume that is true to start. So think of it this way. There are 7 spaces to fill. 5, 6, and 7. These are the 7 digits and or letters on your license plate. This first one we'll call D for digit. These next 3 are going to be L. I'm going to call them L for letters. And then the last 3 will also be D for digits. How many digits are there to choose from? There are 10. How many letters in the English language we're talking here? How many letters are there to choose from? 26. And so we can reuse the letters. We can reuse these things. It's going to be 26 and 26, and we'll have 10, 10, and 10. So at this point, it's a matter of multiplying that all together. Let's get out a calculator to do that. So this is going to be, looks like 10. I can change the order that I multiply things in. That's okay. That's the commutative property of multiplication. So I can multiply all the tens together. I'm going to get 10,000. Makes sense. The 1 with 4 zeros after it, since I'm multiplying 4 tens together. That should make sense. I can multiply this by 26 3 times. Could I do 26 to the 3rd times 10 to the 4th? Would that also work? Yes, it would. So this is going to work either way. If this was a bigger number, if there were more 10s multiplied than just 4 and more 26s than just 3, I may have used powers instead of multiplying each individually, but either way you do it, you should get the right answer of, this is going to be, if I put commas here, a comma there, and a comma there, so 175,760,000 license plates. So it looks like we should have the whole state of California covered pretty good. So license plates, we don't have that many people. Sometimes it feels like we have that many people here in California, but there's actually over 30 million people here in California last I checked, but not 175 million. And we're going to assume that not each person even has a car, and so this should be totally enough. Do people get these custom license plates that wouldn't fit this description? Yeah, we're just assuming the general ones, what is possible. So part B, if repetition now is not allowed. So a slightly different problem here. Repetition not allowed. We're going to be taking away some choices now, so you would expect to have a smaller number than what we had here. So let's redo what we did before. Start it off the same way. So digit, letter, 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 digit, digit, digit. So how many digits do you have to choose from at the beginning? If repetition is not allowed, you have 10 to choose from at the beginning. But then the next digit, let's just jump to that right now. What the next digit would be filled in with would be, you would have 9 choices for that digit. No longer 10, but 9. You are not, in a sense, not replacing the digits. You can't use the same digit again. So this is the same sort of concept as a without replacement problem. So 10 times 9 times, this would be 8 now, 8 choices, times 7 choices for the last one. Letter-wise, you're going to have 26, and then 25, and then 24. Still multiplying it together, still using that counting principle where we multiply the total number of ways all together, get multiplied all together for our total number of choices. Definitely going to want a calculator for this one. Let's see what that is. So we have 7 completely different numbers. I just dropped my pen. There we go. 7 completely different numbers to multiply together. What just happened there? I don't know. It's whoa! Never tried that before. It's reading the back of the slate that I write with. That was weird. I had my pen pointing it towards the back of it. Anyway, 10 times 26 times 25 times 24 times 9 times 8 times 7 is going to give me that. Did I get them all? Yep, looks like I got them all. So 78,624,000. 78,624,000 license plates. So still quite a few, but considerably less without repetition. No repetition allowed. And I'm going to insert a page in here. I need one more page for part C. Okay, let's say repetition is not allowed. Let's stay in the same. Repetition is not allowed. And one more thing, and the last 2 digits must be, we're going to say they must be 34. So the last 2 digits have to be 34. So let's do the same sort of thing again. Put 5, 5, 7. Put 7 spaces. 7 spaces. There we go. And this first one is a digit. The last 3 are digits. And these 3 are letters. So how many choices do you have for these last 2 digits? You just have 1, because that second to last digit has to be a 3. So there's only 1 choice for that. The last digit has to be a 4. There's only 1 choice for that. So this is going to be 1 times 1. So repetition not allowed. That would mean for the first digit, would you have 10 digits to choose from? Excuse me. No, because you've used 3 and 4. Those have to go here. So you cannot select 3 and 4, meaning that you have 8 more digits left to choose from. So 8, and then this one is going to be times 7 right here, because you can't use whatever you pick there. You can't use that anymore, so you're going to have 7 choices there. These are still the same as before, the 26, 25, and 24. And so now we multiply this all together, and let's see what that gives us. So we have 8 times 26 times 25 times 24 times 7. I'm going to leave off the times 1 because that's not going to change anything. So I have 873,600 license plates. So a lot less than before, because these 2 digits were already chosen, already selected for you. You couldn't change that. In a different color, so you don't forget where these came from, let's write off to the side here a little note. So 8, there's only 8 digits left. So that's where that number came from. And then the 7, there were only 7 digits left. And let's move on. Let's check out some definitions now. So we're going to define what a permutation is. Let me just double check this. I think I got everything there I wanted. Yep, we're good to go. So a permutation. Before I define the word permutation, I want to bring up something. I want to bring up a dictionary, on my dictionary, defining what the root word is, permute. What does permute mean? If you can remember what permute means, that will help you remember what permutation means. And so here it is. Permute means to change the order of. So if you can remember that permute means to change the order of, then you can remember permutation means it's things going in order. It has to be in a certain order. Order makes a difference with permutations. Order makes a difference. Remember that. If you remember nothing else about the word permute, remember order. Order makes a difference. So any permutation is any ordered. I'm going to double underline that because it's that important. Yes, yes it is. Any ordered arrangement of a given set of objects. And then one other thing to define here, the number of permutations of n distinct items is this. Now you don't read that N, it's not N! No, it's not a really loud exclamation point. No, that's not what it is. You read this N factorial. Calm down, Mr. Wagner. It's not N, it's N factorial. Where, so this is not an exclamation point in mathematics, where, but I just say it for fun, okay? So where n factorial is equal to n times 1 less than that, n minus 1, times 2 less than the original one, 1 more less than the previous one, n minus 2, times, and that keeps going, that pattern, until you get all the way down to 1. You keep putting these in parentheses to keep it consistent there. So what does this mean? Let's box this in, but what does this mean in terms of a problem? Let's check out example 2. Let's see what we got. So example 2. Suppose the letters S, P, A, C, and E. What kind of E is that? And E are placed in a hat. Oh, I see what you did there, Mr. Wagner. That's clever. That's space. That spells space. In a hat and selected at random without replacement. So we are not going to put the letters back without replacement. Party. How many ways can all 5 letters be selected and arranged? So the arrangement, the order, makes a difference. This is a permutation problem because of that. So be selected and arranged. So you're going to have, you can think of it this way. So let's do this right now as we begin to get the hang of this. I'm going to put 5 spaces here, and for that first choice, these are all letters. That first choice, you're going to have 5 choices. You're going to have 5 letters to pick from. An S, a P, an A, a C, or an E. So you could have any one of those 5. So 5 choices to start. Now you've picked that one letter, you only have 4 more left in the hat to choose from. It could be this one, this one, this one, this one, or this one. It doesn't make a difference which one you pick. You had 5 choices to choose from to begin, and now you've only got 4. And then you've only got 3, and then you've only got 2, and then you've only got 1. So how can we simplify this? How can we say this easier? This is the same thing as 5 factorial, or 5 if you want to have fun with it, which equals what you see here, 5 times 4 times 3 times 2 times 1, which is, we take, this is 6, 6 times 4 is 24, 24 times 5 is 120. So 120 include units or what you're talking about. This is saying how many ways could this happen. So put 120, put the word ways after that. Show me what you're talking about there. And then part B. Let's change it up just a little bit. How many ways can only 3 letters be selected and arranged? So how many ways is possible for that? So you're going to have 3 blanks to fill in now, which is going to be how many for the first one? 5 still. How many for the second one? 4. How many for the third one? 3. And there's 2 poor letters that just get left out and don't even factor into what we're doing here. Those poor letters, whatever ones they were, we're very sorry for those letters. But what does this equal? This equals 5 times 4 is 20. 20 times 3 is 60. So we have 60 ways. And that should make sense too, because this one we just multiplied by 2 more. 60 times 2 would have been 120. Times 1 doesn't change anything. So 60 ways. And so I'm going to write an equal sign here in a different color. Please put this in a different color. We're going to see another way to do a problem like this down here. So we're kind of introducing that right here. Let's see what it is. Yes, this is big box time here. Permutation formula. This is pretty darn important. So the permutation formula, what is the permutation formula? What does it say? You may see a little button like this on your calculator somewhere. N, so lowercase n, it is a subscript, so it's small, it's written beneath. It's not a power, it's not up here. Okay, so little n, capital P, little r. This is a permutation. So this permutation, order matters, permutations, is n factorial, or n over n minus r factorial, or n minus r. Some of you may have parents that are hearing this and be like, what is Mr. Wagner doing over there? Why is he yelling at my student, my child? I don't appreciate this. If you're reading this out loud, you're going to read this. It's not NPR. It's not the radio station, okay? It's read like this. It's the number of permutations of n taken r at a time. So that's in a different color. Put that off to the side. NPR, order matters. So we're going back to up here. I want to show you how this matches up with what we have here, and then we'll do another one like that. And so this equals different color now. this is the same thing as 5 permute 3. I think that's a way we'll say it sometimes too, rather than saying the number of permutations of 5 taken 3 at a time. You can read it like that, or we can just say 5 permute 3. I'll also say it like that too. And so this is going to equal, we'll put it into the formula. It's 5 factorial, or, no, I will, 5! I'm kidding, I will do that. Okay, 5 factorial over 5 minus 3, 5 minus 3, n minus r. Factorial! Woo! Alright, 5 factorial is the same thing as 5 factorial. 5 minus 3 is the same thing as 2. So we have 5 over 2! And this becomes, you can write this as 5 times 4 times 3 times 2 times 1 over 2 times 1. And if you have 2 times 1 here, that'll cross out with the 2 times 1 here. And what are you left with? You're left with 5 times 4 times 3. Amazing! That's right over here. 5 times 4 times 3 is 60. So we've already done that. This is an alternate way, the permutation formula way, to think about this one. Very clever, very slick. Let's check out a third example. So you are going to become a little world traveler as a college student. Let's assume that's true. So as a college freshman, you decide, making a good decision here, I think. You decide you want to take a trip to a new country each spring break. Good decision. Go explore the world. Go learn about a different culture. Take something back from them. But just don't steal their things. I mean, take something valuable from them in terms of learning from them. How's that? Yes, sounds good. So, however, you have a list of 7 countries. That's not going to work unless you go to college for 7 years. Let's assume that doesn't happen. So you have a list of 7 countries. Maybe you're going to be a doctor. Maybe that could happen then. But you want to visit, let's say you're just going for your bachelor's degree here. So you want to visit 7 countries you want to visit, but only plan to go to college for 4 years, like the typical college student tends to do. How many different ways can you schedule a visit to 4 of the countries? So you've got 7 countries you want to go to, but you can only pick 4 of the countries. Is order going to matter in this situation? Yes, you're saying scheduling, so you're going to say that I'm going to go to this country first, and this country next, and this country next. We're going to say that, suppose you went to Spain, and then you went to Australia. That's going to be different than going to Australia first, and then to Spain. The order is going to make a difference here. So how many different ways can you schedule your trips to these countries? Okay, so how many different ways can you schedule a visit to 4 of the countries? SOLN. Let's solve this bad boy here. Let's see what we got. So the solution, what are we going to do? You're having 7 to pick from, and you're going to pick 4 of those things. That would be a problem like this. 7 permute 4. So of 7 things, how many permutations do I have if I only pick 4 of those things? So I've got, this becomes, go back to your permutation formula. Number of permutations of 7 taken 4 at a time is going to be 7 factorial, or 7 over 7 minus 4 factorial, or 7 minus 4. And that's going to be 7 factorial, or 7 over 3. And that's going to equal, I'll show you a couple different ways to do this. This is the long way. 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. So that's the long way. Here's the shortcut way. You can think of it this way too. 7 times 6 times 5 times 4 times, maybe it doesn't seem so short right now, but we're going to simplify it like that, times 3 factorial over 3 factorial. That's the same thing here. Watch this. This is slick. 3 times 2 times 1 cancels with 3 times 2 times 1. 3 factorial cancels with 3 factorial. So instead of writing the whole thing out, you can just write it like that and cancel it out like that. So what are you left with? You're left with 7 times 6 times 5 times 4. And let's see if we can do this mentally. This would be 20. 20 times 6 would be 120. 120 times 7, you'd have 700 plus 140, which would be 840. Yes, so 840 ways to schedule your trips. And I wanted you to write one thing here as to why you can do this. If you want to just go right to this step from something like this, you're welcome to do that. This is the shortcut way. So feel free to skip this step if you understand why this is the same as this. If you're not comfortable with that, write the whole thing out. You can cancel out that way too. And we're going to check out one more twist on this idea of permutations. And this part I'm going to do in green. I just want you to listen right now. Just listen. Put the pencil down, put the pens down. Just listen until I tell you to do so. So just watch this, and I don't know if you'll be amazed, but hopefully you'll understand what's going on at least. So how many different things do I have here? Well, I've got 3 letters, but 2 of them are the same. Interesting. I've got one blue D and I've got one red D. So if you were doing this permutation-wise, how many ways are there to arrange these 3? You're just listening right now again. So you've got 3 spaces to fill. You could have 3 choices times 2 choices times 1 choice, which would be 6, the same thing as 3 factorial. What are those different choices? I'm going to, or how can I arrange those different things? So I'm going to copy this 6 times. Here's 1. Nope. I'm just going to use my keypad for this. So duplicate that. There's 1. Duplicate that again. There's a second one. I'm going to rearrange the letters in just a moment. So here's a 3rd way, a 4th way, 5th way, and a 6th way. Okay, so these are not different yet, but I think, yep, I can just rearrange like this. So this is one way to do it. D-A-D, dad. I could put this, I could flip-flop these around. So D, D-A. I could put like that too. Actually, I just thought of a good idea, I think. I'm going to flip-flop the blue and the red. And so, in some ways, if color mattered, this would be different than this. But if color did not matter, this would be the same as this. You could also write it as DDA, and you could put the blue D first, or you could put it second. You could flip-flop those. Or you could say ADD. I didn't even think about that, but maybe some of you are having trouble listening to the notes because that's something that you have. So hopefully you can take a little break, pause if you need to, remember. So if you have ADD, do what you need to do to stay focused. And I'll try to do my part, keep it interesting as I can. So ADD, DDA, go away, bye, go away, hello, go away. Okay, there we go. These are the 6 ways you could arrange these. However, wouldn't you say that if color did not matter, that this is just one distinct possibility, DAD, dad. And then DDA is another distinct possibility. And then ADD is the third distinct possibility. So this 6 is kind of misleading here. Is it 6? Well, yes, if the color made a difference, but what if the color didn't make a difference? Then it would just be 1, 2, 3 different ways to write this, and that would be it. So how do we compensate for that in terms of permutations? Duplicate objects. There's another formula, final formula we have here. I want you to not write this down. That's up to you. I guess you could if you really wanted to, but time to pick that pen or pencil up again. Hopefully a pencil's better. If you make an error, you can erase that error and fix it. But permutations of duplicate objects. Permutations of duplicate objects. How do we deal with those? Here's how we do it. So the number of distinct permutations of n objects where n and then a little 1, n sub 1 of the objects are identical, n sub 2 of the objects are identical, and that pattern was going to continue. So n sub 3, n sub 4, and so on, all the way up to n sub r, the last one, n sub r of the objects are identical is found by this formula, found by the formula you'll see right here. So this is the big thing to remember. So n goes on the top, n factorial, and then n sub 1, n1 factorial, n sub 2, n2 factorial, times all the way through to n sub r, or n sub r factorial. That's the big thing to remember here. So I'll circle that within here. And so if we put that into practice up here, this you don't have to write down again. I'll use the green. We didn't actually have 6. We only had 3 to choose from. So we have a total of 3. Does this match up with this? Well, we had 2 of the identical objects. So n sub 1 is going to be 2 factorial. And this is the only one that is repeating. The only one that shows up more than once is the d. So this would become 3 factorial over 2 factorial, which is the same thing as saying 3 times 2 factorial, 3 times 2 times 1, over 2 factorial, 2 times 1. These would cancel. You'd be left with 3. And that's exactly what we see here. So we're going to do one more example like that. This one I do want you to write down. And that's right, more yelling, more yelling here. Jack Nicholson in the movie A Few Good Men, he gets really upset in the courtroom and he's like, "You can't handle the truth!" And he, I think, does he say that to Tom Cruise? It's an older movie. You may not have seen it. I haven't even seen the whole thing. Shame on me. But why did I use that? Oh, you will see just a moment in how many different ways can the letters of the word, crazy word here. You've heard of the word fallacy before, I hope. So the word fallaciousness. Fallaciousness. How many ways can they be arranged? So back to the dictionary. What does fallaciousness refer to? Fallaciousness is a noun. Fallacious means containing or based on a fallacy. Fallacy is something that is false assumption or something that's just wrong, and so tending to mislead or deceptive. That's why Jack is so mad here. You can't handle the truth. You're just a fallacious person. You are all about fallaciousness. Okay, here's the solution. So, besides not being able to handle the truth, can we handle this math problem? Let's see. Of, not on, but of the 14 letters. There are 14 letters here if you count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Of the 14 letters, if we just said it was 14 factorial, we would be kind of double counting certain ones, because the L and L, if I flip-flop L and L, it's still L and L. We're saying it's not like a different color letter or something like that, like we had with the dad back here. We're saying that FA, this L is the same as saying FA, then this L and this L would spell the same thing, would give the same thing. So, of the 14 letters, there are 2 A's. I'm looking for repeating ones. There's 2 A's, 1, 2. There are 2 L's, and there are 1, 2, 3 S's. The rest do not repeat. So 2 A's, 2 L's, 3 S's. Thus, the number of possible arrangements is, go back to this formula. So now this becomes a lot more helpful. This would be insane to try to write down all the different possibilities of this. Crazy, crazy, crazy. You would need I don't know if you would need a computer to do that, but you would definitely want a computer to do that for you. There's going to be a crazy amount of different arrangements. So we're going to use this formula to determine how many of those arrangements there are, and not write them all down. Okay, so this becomes, well, there's 14 to choose from. So on the top, you have 14 factorial. You can yell it out if you want. This would be, there's 3 S's. So I'm going to have 3 factorial. This is kind of my n sub 1. There's n sub 1 of the objects are identical. So 3 that are identical. N sub 2, that's the second group. I had 2 A's, and I have also 2 L's. So I'm going to have this times 2 factorial times another 2 factorial. That's coming from here, here, and here. If I were to write this all out, let's do that. So it's 14 times 13 times 12. Ooh, man, we're going a long ways here. Times 10 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over, then 3 factorial is just 3 times 2 times 1. So I'll kind of, just to make the point that it's just coming from here, I'll put that in parentheses for now. The 2 factorial would just be 2 times 1, and the other 2 factorial would just be 2 times 1. Do you really need the ones? I could see you leaving those out. You should know that it means all the way down to 1, but you don't really need to include the ones when you're doing this later. I think it's a good idea, though, just a good habit to get in the practice of, so that you know what's what. And then let's see what we can cancel. I see 3 times 2 times 1, and I see 3 times 2 times 1 right there. So I could cancel that whole group with that whole grouping right there. And then if you put this together, let's use our different color here to make a clear point, a clearer point. 2 times 2 would be 4. And so I could get rid of the 4 here with the 2 times 2 here. And once that's done, all these 1s, I don't have to think about the 1s. There's nothing left on the bottom except just a 1, 1 times 1. And so I can get rid of the denominator because of that. And so this becomes 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5. Easier to do the cancellation first before you try to multiply it all out and then try to cancel from there. Definitely easier to do that. I don't know why I'm writing a bar there. I don't need my denominator anymore, so that is gone. So I can just put this into a calculator. This is actually the same thing as saying, well, that would be 14 factorial. This, because of the way it canceled, you could use this sort of idea. It would be 14 factorial over 4 factorial, because the 4 factorial is gone, but that's just a little side note. So 14 factorial divided by 4 factorial. I'll show you in class how to use your calculator to find the factorial button, and to also, if your calculator has this function, to find this permutation button. Some of your calculators will have that, and we'll talk about that in class, how that all works out. But for right now, let's clear this out and just do this the longer way. So 14 times 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 is going to equal, whew, big number. This is a comma here, a comma here. We're in the billions. So 3,632,428,800. 428,800. So if you took all the letters in the word fallaciousness and you put them in different arrangements, distinct arrangements, where the order matters, but repeated letters doesn't mean, if you switch the order of these two things around, it's not a different thing there. There are this many arrangements. That is the total number of arrangements possible. So 3,632,428,800, lots of arrangements for sure. And that'll do it for this lesson. We'll talk about some questions in class, and again, we'll review or check out your calculators to see if we can find how to use or find where the buttons are for some of these shortcut buttons for us here. Hopefully that helped you. Go back and review if you need to. Have a good day, everybody.